Hey everyone, and welcome to this explainer. I am absolutely pumped to dive into today's topic with you. You know, if you've ever felt completely bogged down by the overwhelming grind of learning algorithmic patterns, well, today is the day we change that. Our core mission right now is to take one of the absolute most powerful concepts in computer science and turn it into a single, masterable superpower. We are going to completely demystify the dictionary, hash table, and set pattern, and we're drawing directly from the incredibly brilliant distilled notes found in Amon's AI journal.
Okay, so let's just jump right in and address the elephant in the room. We've all been there, right? You write what you think is a perfectly logical, functioning algorithm, only to hit submit and get slapped in the face with that dreaded time limit exceeded error on LeetCode. Honestly, it's the worst, and the reason these brute force solutions fail is almost always because they rely on nested loops. They're forcing the computer to check every single possibility against literally every other possibility. And well, as your data grows, the time it takes to compute all of that skyrockets exponentially. It is an absolute pain, and it's exactly the trap we want to avoid.
To really visualize why we need a better way, think of your data like a massive library. A nested loop approach, that O of n squared trap, means you're walking into every single room, checking every single shelf, and reading the title of every single book until you find the one you're looking for. It's exhausting. But if we use a hash table shortcut, that gives us O of n time overall with O of 1 or constant time lookups. Think of this as walking into that same massive library, asking the magical librarian for your book, and having them just teleport it directly into your hands. Instantly. No searching required. That right there is the pure magic of O of 1.
So here is our roadmap for today. First, the magic of O of 1. Second, counting and frequencies. Third, mapping relationships and states. And finally, number 4, advanced dictionary architectures. Let's get right into it.
Section 1. The magic of O1.
Drawing straight from Amon's AI journal, in Python, we have 3 heavy hitters that give us this teleportation-like speed. First up, dictionaries, which map keys to values. Second, sets, which store only unique elements. And third, counters, which, as the name implies, automatically track the frequency of items for us. The absolutely crucial point to remember here is that under the hood, they all use hash tables. This means whether you're checking if an item exists, grabbing its value, or updating its count, it happens almost instantaneously, totally regardless of how much data you throw at it.
Moving on to Section 2, counting and frequencies.
To really prove the incredible versatility of just simple counting, Amon's journal highlights a few classic LeetCode problems that basically crumble under the weight of a basic hash table. We're talking about finding the number of good pairs, solving palindrome permutation, or checking for a unique number of occurrences. Now, in the brute force world, these would require multiple passes or clunky nested loops just to compare elements. But with a dictionary or a counter, you just pass through the data a single time, tally things up, and honestly, you're practically done.
Take the palindrome permutation problem as an example of this elegant logic. How do you actually know if a string could be rearranged into a palindrome? Well, a palindrome reads the same forwards and backwards, right? Which means the characters have to appear in matching pairs. You can have at most one character sitting right smack in the middle that appears an odd number of times. So, a simple counter turns a seemingly complex string evaluation into 2 incredibly easy steps. Step 1, count the character occurrences using your hash table. Step 2, just check that no more than one character appears an odd number of times. Boom! O of n time, O of 1 space. It's absolutely beautiful.
All right, Section 3, mapping relationships and states. Let's break down subarray sum equals k. This is a notoriously tricky medium-level LeetCode question. You have to find how many continuous subarrays add up to a specific target number, k. If you try to check every single possible subarray, it's going to take way too long. So instead, we use a dictionary to store the running sums we've seen so far. As we iterate through the array, we calculate the current running sum. Then we just ask our dictionary, hey, have we ever seen a previous running sum that perfectly equals our current sum minus k? Because if we have, it means the elements between that previous point and our current point add up exactly to k. And definitely notice step 1 here. We initialize a 0 in the hash map. Why do we do that? Well, because if our current running sum is exactly equal to k right from the very start of the array, sum minus k equals 0. That initial 0 acts as our mathematical baseline. It's just a brilliant single-pass solution.
Oh man, I absolutely love this next one. This is a massive aha moment from the diagonal traverse problem. The problem asks you to iterate through a 2D matrix diagonally. Sounds like a total nightmare of edge cases and bounds checking, right? But Amon's AI journal points out a pure mathematical relationship that is just mind-blowing. The sum of indices on all diagonals are equal. Seriously, let that sink in for a second. If you're at row 0, 2, the sum is 2. If you're at row 1, 1, the sum is 2. Row 2, 0, the sum is 2. They are all sitting on the exact same diagonal. So you literally just loop through the matrix normally, use a dictionary where the key is the sum of those indices, and append the elements to that key. The dictionary beautifully groups the elements for you using nothing but pure math.
Which brings us to Section 4, Advanced Dictionary Architectures. Let's talk about the infamous LRU cache, or least recently used cache. The problem specifically demands that getting and putting items has to happen in O of 1 time, while you also keep track of the order items were used so you can easily evict the oldest one. If you try to just use a standard queue or a deck, finding out if an item exists so you can update its position is really slow. But by using an ordered dictionary in Python, which is essentially a doubly linked list mashed up with a dictionary, you get the best of both worlds. You get the O of 1 instant access time of a hash map, plus built-in methods like move to the end to easily manage the recency of the items. The dictionary-backed ordered dictionary wins heavily here in both performance and code simplicity.
Honestly, this next example is probably my favorite trick in the entire journal. A trie, or prefix tree, is a data structure used heavily for things like search autocomplete. Usually, you build this by creating a really complex custom node class. But guess what? We can bypass that custom class entirely. You can implement a trie super elegantly using just nested dictionaries. Each key is a letter, and its value is simply another dictionary containing the next possible letters. To mark the end of a valid word, you just add a dummy key, like a hyphen, to that nested dictionary. It's incredibly fast, requires way less boilerplate code, and heavily leverages the highly optimized hash tables built right into Python.
Finally, Section 5, Spotting the Hash Pattern.
So, how do we actually spot this in the wild? The crucial point is learning to recognize the signals hidden inside the problem description. Based on all the LeetCode problems we've analyzed from the source material today, here is your definitive checklist. You should immediately start thinking about dictionaries, sets, or counters when you need instant O of 1 lookups instead of constantly scanning through arrays. When the core task involves counting frequencies of characters or numbers. When you need to group related elements together, like shifting strings or those matrix diagonals we talked about. Or when you need to track historical, seen states, like prefix sums or previous transactions, so you can reference them instantly later on.
And just like that, we're at the end of our journey today. We've taken the somewhat abstract concept of hash tables and transformed it into a concrete, highly applicable superpower. You now hold the key to unlocking true O of 1 time complexity. So, I really want to leave you with this provocative question to chew on. What brute force, nested loop code in your current project are you going to go rewrite today? Seriously, go find those bottlenecks, drop a dictionary in there, and watch your code absolutely fly. Thanks so much for hanging out and learning with me on this explainer, and I will see you next time.